In this video, we are going to look at and prove Euclid's lemma. And Euclid's lemma says that if P is prime, it's a prime number, and P divides A times B, then P divides A or P divides B. So let's look at an example of what's going on here. So Euclid's lemma needs to look, we need a prime. So let's say we're looking at a prime P equals 3. And let's say that A is equal to 6 and B is equal to 10, then it is true that 3 divides 6 times 10. 3 divides 60. That is certainly true. And so Euclid's lemma says since 3 divides 6 times 10, it must be that either 3 divides 6 or 3 divides 10. And yep, it's true. 3 actually does divide 6. It doesn't divide 10, but only one of those two things has to be true. This only works when P is prime. We can only draw the conclusion when P is prime. And here's an example that illustrates what can go wrong if P is not prime. So let's say we are looking at 4 and still A equals 6 and B equals 10. It is still true that 4 divides 6 times 10. 4 divides 60. 60 is 4 times 15. But does 4 divide 6? No, it doesn't. It doesn't divide 6. And 4 also doesn't divide 10. And if you like, you can think about a little bit what goes wrong here when P is not prime. It has something to do with prime factorization, and we're going to look at the fundamental theorem of arithmetic a little bit later that sheds some light on this. But at this point in time, all that I wanted to illustrate is what Euclid's lemma says. So that if P is prime and P divides the product of two integers, then it has to either divide the first one or the second one of those integers in that product. So let's go ahead and prove. This is our first proof. All right, very good. How do we start? We start with the hypotheses. Okay, so let P be a prime. And suppose that P divides A times B, our hypotheses. How do we prove something like this? Well, in this case, since our conclusion is P divides A or B, we can start by saying we have two cases right here. So case 1 is P already does divide A, and then we are done. So if P divides A, then we are done. Seems a little bit like cheating, but it's something that we can consider. If P already divides the first one of our two integers, then, well, the conclusion is true and there's nowhere we need to go. The more interesting case is case 2, and that is if P doesn't divide A. Then what? Well, then we have to show that P divides B, so that our conclusion is still true. And this is what we're going to do. So let's assume P doesn't divide A. So if P doesn't divide A, and since P is prime, what can you tell me about the GCD of P and A? That GCD has to be equal to 1 since P is prime, right? so it doesn't have any other divisors, and it doesn't divide A, so the GCD between A and P has to be equal to 1. But if that's the case, then we just learned in the previous video, we saw the theorem 0.2 that said that we can write the GCD of two numbers as a linear combination. So thus there exist integers s and t such that we can write our GCD as a times s plus p times t. That was the statement in theorem 0.2. So this is true by theorem 0.2. And how is this helpful? We need to show that p divides b. This is where we are going. And if you remember from earlier, what does it mean that p divides b? It means that we can write b as p times something. And that's where we are headed. So we want to write b as a multiple of p. b is nowhere in sight in our equation right here. So we are going to make it appear by multiplying the entire equation by b. So if I do that on the left-hand side, I just get b. And then on the right-hand side, I have two pieces, and both of those need to be multiplied by b. Since we're working with integers right here, I can stick it anywhere I like. So I can write this as ab times s plus pt times b. Doesn't really matter. But really, all that I did right here, we just multiplied by b. Okay, how is this helpful? Well, we have b written as something plus something, and we already have p sitting right here. So if we could make an argument that p also divides that first piece right here, then we are in good shape, because then we can factor out a p, and we have demonstrated that b is p times something, and so that p divides b. What's our argument that p must divide that first part in our sum? You can think about that a little bit. What was our hypothesis? Our hypothesis was that p divides a times b, and that is sitting right here. So a times b is sitting right here. So actually p does divide a times b. How do we write this down as to make our argument really tight? So we can say, since p divides a times b, there exists an integer k such that we can write a times b as k times p. Okay. So if we stick that into our equation, we have b is equal to k times p, and then we still have that s, plus p times t times b. We're almost there. We have a p in both pieces, so we can factor that out. We can take out our p, and then we are left with k times s plus t times b. And that means that p divides b. And that's what we wanted to show. So we are done. We are done with our proof. Our first case was if p divides a, we are done. Our second case was if p doesn't divide a, then we have shown that p divides b, and that takes us back to the statement of our theorem. So we've shown that if p is prime and p divides a times b, then p divides a or p divides b. We are done. Q, E, D.